Greetings, everyone. It was recently my pleasure to be a guest on the podcast PodCAT, which is a predominantly chemical engineering podcast focused on catalysis. I am not really a catalysis person, but the hosts, my colleagues, Mark Porosoff, Tom Senftel, and Ezra Clark were kind enough to have me on, and I think we'll actually do a crossover episode, and they will be on this channel and my podcast, Molecular Podcasting, in the next few weeks. And I would encourage everyone to click the link here to subscribe to their podcast, and you can do that anywhere podcasts are found. And I think a lot of the topics that they cover in terms of resources for early career researchers would also be interesting and useful to our own audience. So I'm going to wait here for a few seconds while you go ahead and click that subscribe link. I guess that's, you could make that one word, clink it. You could clink it, and I'll give you an opportunity to do that now, and then I'll give you the bonus episode of the video feed from the podcast that we did on PodCAT for all your catalysis needs.
Welcome to PodCAT, your one-stop shop for all your catalysis needs. I'm Mark Porosoff.
I'm Tom Senfley.
And I'm Ezra Clark.
Today, our special guest is Professor Darren Lipome. He is a professor of nanoengineering, chemical engineering, and materials science at UC San Diego. He is also the Associate Dean for Students and the Faculty Director of the IDEA Student Center at the Jacobs School of Engineering at UCSD. He is the incoming chair of chemical engineering at University of Rochester, scheduled to begin his term in July. Darren earned his bachelor's degree in chemistry with a minor in physics at Boston University with a PhD in chemistry at Harvard from George Whitesides. He did his postdoc with Zen and Bao at Stanford and started his independent career at UCSD in 2012. He's the recipient of numerous awards. I'd like to highlight the Air Force Office of Scientific Research Young Investigator Award, the NIH Director's New Innovator Award, and the PCASE Award. Darren hosts a podcast, Molecular Podcasting with Darren Lipome, and has a YouTube channel with over 16,000 subscribers and nearly 1 million views. It is a pleasure to welcome Darren Lipome to PodCAT.
Pleasure to be here.
Yeah, thanks so much for coming on. And so we kind of like to start our podcast with just getting a sense of what got you into academic science, how your research interest developed, and how you ended up where you are today. So if you could just tell us a little bit about your career trajectory, our listeners would love to hear.
Science to me growing up was the legitimate route to magic. And I remember watching 3-2-1 Contact on PBS, and the popularizers of science do a really good job at not telling young people about all the bookkeeping that constitutes 90% of scientific research. And so it's about lasers and stars and black holes and DNA and zoology and David Attenborough stuff. And it all seems so magical. And to me, science was just that's how you made a lightsaber. That's how you made a holodeck. And that was the impetus for my childhood interest in science. When I got to high school, I had a great chemistry teacher. His name was Tom Dowd at Hilton High School, which is northwest of Rochester. And he had a way of making chemistry come alive. And it was in part his charisma, but in part the way that chemistry in particular interacted with my kid's brain. I really enjoyed the way that elements could be personified. So fluorine is the most greedy atom. It wants all of its
Mhm.
electron density close up to it. And so when I got to college, I really enjoyed organic chemistry. I joined an organic synthesis lab in which I got to use a number of heterogeneous catalysts. And I think chemistry, reaction engineering, later on materials engineering, was the center of the bullseye for me in the scientific milieu. I think biology, at least to learn it, involved too much memorization, and physics involved too much math. But chemistry was just where it was at. And one of the most intelligent things that I ever did unintentionally was get my chemistry work called engineering. So in grad school, I worked in a famous chemist's lab, but the work that I did was in kind of top-down fabrication engineering, sort of alternative approaches to photolithography to make small structures that had interesting optical and electronic properties. And then I joined as a postdoc the lab of another chemist, but she is a rather well-known chemical engineer, although you folks may not consider people who didn't have a chemical engineering background a true chemical engineer. But I was able to rebrand my work as materials engineering at best, and maybe a little bit into chemical engineering, and then I got an appointment in a nanoengineering department with a chemical engineering program, and our department's actually going to be renamed imminently Chemical and Nanoengineering. So that's my career arc.
Mhm. Yeah, that's I mean, I think it really depends how you ask, but we try to be inclusive on PodCAT. So I think we consider you a chemical engineer here.
Oh, thank you.
Yeah. Yeah.
It's an
So
honor.
so in getting into academia and starting your own independent career, what kind of led you down your specific research interests, and what do you think was your first big break in your field?
I was fortunate enough to have some undergraduate funding from the Beckman Scholars Program. And there was a symposium in 2003, first time I had ever been to California. And the late Rick Smalley gave a talk on energy and how it's a classic Nobel Prize syndrome. When you win a Nobel Prize for one specific topic, that is the discovery of the fullerenes, then you think you can talk about any topic in the world with authority. And in Professor Smalley's case, he absolutely could speak with authority on so many different topics. And he explained to the audience how the availability of energy could solve all the world's problems, where if you didn't have enough water, you could desalinate lots of water. If you had access to energy, you wouldn't be so reliant on natural resources like if you get a lot of solar energy, you wouldn't need to extract so much petroleum, and that really resonated with me. But at the time, I was in an organic synthesis kind of medicinal chemistry lab, and I'm like, how can I use my interest in organic structure to influence the energy challenge, or to affect the energy challenge? Then the following year at the same symposium, Nate Lewis from Caltech gave a talk on organic or chemical challenges in renewable energy technologies. And I went up to him afterwards, gave him a really sweaty handshake, and I asked him, what can I do as an organic chemist? He said, well, there's something called an organic solar cell. And so when I went to grad school, there was a cohort of really talented postdocs, Ryan Checky, Michael Dickey, and Emily Weiss, who were interested in organic and quantum dot photovoltaic cells. And so this sort of seeded my interest. One of my papers in grad school was on a really, really crappy type of organic solar cell that had kind of an interesting structure. We called it the jelly roll. Anyway, my advisor hated that project, but he let me publish it because, I don't know, he felt bad for me that it didn't work so well, but it had a cool name, I guess. And so then when I did my postdoc, there was sometimes you just have to follow the funding. And I was interested in energy. I was interested in making and designing materials, but there was a postdoc fellowship in flexible, stretchable electronics from the from the CIA, actually, the Intelligence Community Postdoctoral Fellowship Program. And so that project was about carbon nanotubes. Thinking of Rick Smalley, but anyway, that project was about carbon nanotubes. But then I'm like, well, I'm interested in pi conjugated organic structures. How about we make rubber-like organic semiconductors? And so at the time, there was a lot of work on flexible, stretchable electronics, but none of it was intrinsic. It was all, how do you get little metal traces to be serpentine and wavy and buckled so that when you stretched it out, it would unfurl. And that's how elasticity was designed. But I'm like, if we're organic, people interested in organic materials, we should be able to make entropic springs out of our materials. We should be able to design the structures so that they retain their charge transport under significant mechanical deformation. And so in my postdoc, we just kind of stretched a whole bunch of stuff, and everything's stretchable, it just might not survive after it's stretched. So then in my independent lab, I'm like, okay, we're going to do a deep dive into molecular structural property relationships that give rise to favorable mechanical properties while retaining charge transport. So that made me interested in more continuum mechanics and also microstructural analysis and spectroscopic and X-ray tools and how to understand how these properties could be retained. From that interest in mechanical properties of organics, we applied some of that work to mechanical biosensors, so implantable and wearable materials. And then those interests combined into kind of my newest interest in haptic biomaterials, so materials that can be used to understand and manipulate the sense of touch and interoception, the way that we feel mechanical forces in the body.
Yeah.
One theme I kind of notice is that, right, you follow the research across and over boundaries, right? So the difference between chemistry and chemical engineering, we talked about that. And a lot of first-year undergraduate students who are debating about their major, they often ask, should I be a chemist or a chemical engineer or, or whatever. And I often kind of say, well, if you're really interested in research, those boundaries don't really matter that much anymore. And really, if you're doing interesting research, you're probably going to be at the interface between these different fields. And yeah, I don't know, maybe you could comment on the way that academia is organized into these different fields, and maybe moving forward, how we could think about being less organized, so to speak.
Sure. Every field has its undergraduate curriculum and then what we do in the research labs at a research university. And it's important that everybody be trained in a core discipline because that's their entry point into a larger, more expansive world. You have to have some decent competence in one particular area, but then you find when you are trying to innovate, and I think there is a way to try to innovate, and that is to take a few of your competencies, and even if you're not great at any one of them, when you multiply them together, you get big denominators, and then you might be one of the best people in a field that no one's heard of. And if I look back in my own career arc, I knew a fair bit about organic synthesis. So maybe out of all scientists, I'm going to use the pool of all scientists. Maybe I was like 1 in 20 in organic chemistry. Maybe I was 1 in 5 in mechanics. But mechanicians don't really know that much about organic chemistry and vice versa. So now I'm 1 in 100. And then what if I became interested in the way that we perceive mechanical stimuli with our fingertips? And maybe I'm 1 in 5. Now I'm 1 in 500. And no one had ever looked at organic materials chemistry and mechanics and the neurobiology of perception or the psychology of perception, but maybe I'm only 1 in 5 that knows something, and I didn't even have to read that many books. about it. And definitely not get an undergraduate degree. It didn't need to do all those credit hours, but that's a way to kind of get this compounding multiplicative effect in an area where no one else is looking and might be fruitful.
Yeah, that's a really tangible and concise way of putting it, because what we've talked about on this podcast in the past about writing your research statement and distinguishing yourself and how do you stand out from the crowd and where do you fit in, and this idea of your selling yourself as your background. You're the only one who can do this line of research because you're the only one who did this postdoc and then this PhD background. It can really be a way to say, I've created my niche. And I think the way that you explain it with these denominators, that you go from 1 in 5 to 1 in 50 to 1 in 500, that is a really elegant way of putting it.
It does make it hard to find reviewers, but that's the editor or the program manager's problem.
Right.
There's a lot of different views about what someone should do with their postdoc. One view is that you continue working in an area that you're already familiar with. You can hit the ground running and really build that resume quickly. The other view is you go and learn something totally new with the idea that down the road you can blend these expertise. And it sounds like you sit pretty squarely in the second group there. What would you recommend, young folks that are thinking about academia, looking for postdoc opportunities? What would you encourage them to consider along these lines? Would you be a proponent for trying something totally new outside your wheelhouse, or how do you weigh these two kind of opposing approaches?
Speaking of opposing approaches, often the applicant and the prospective PI have opposite views of what the expectations are for the postdoctoral stint. The applicant may have an idea of expanding into a new area, but the postdoc advisor often wants somebody to come in and do a job. And the fact of the matter is, you're probably not going to get hired as a postdoc unless you can at least get your way in the door to fulfill that postdoc advisor's primary need. But once you're there and you are filling that niche that they need, there is often a lot more flexibility than a postdoc applicant thinks there may be, especially if the postdoc lab works in a few different areas or applies their area to a few different types of collaborations. And that's a good way to expand your skill set.
That's a really good point. I remember when I was applying for postdocs, I'm an electrochemist. I got interested in microbiology, and I actually emailed a few people that were looking at the intersection of electrochemistry and microbiology, although they were much more squarely in the microbiology space. And I remember just getting rejected so quickly that I didn't even know what happened. So that's some good advice.
I would say that, similar to your experience, Ezra, the PhD students from my group who have gone on to do postdocs have used their PhD expertise to get the job and then diversified after that. I just had the pleasure of going to University of Arizona Department of Chemical Engineering and Environmental Engineering, and I have actually two former students who are PIs there, and neither one of them is doing anything close to what they did as members of my lab, which is very gratifying, which means that I trained, at least in those cases, generalists, people that were interested in looking outside their core expertise.
So when you're looking at wandering into a new area, are you driven by curiosity, or are you driven more by potential impact, applications? Like what is the motivating stimulus for you to go into a new area?
It's hard to say. Sometimes I just drink too much espresso at a conference and I go into a session. And a lot of times it's the speaker will use a particular phrase. And I think language is very intimately related to our ability to synthesize ideas. Sometimes you don't know what you are, you know, sometimes you don't know that there are connections between fields, or that the work that you're doing can be called a particular thing, and then it opens up this new language, right? And once you start applying these words have other connotations, and you can think about it in other ways. Let me give you an example. You know, I'm having the impression, going to some of the meetings with folks in my new department, Mark's current department, about how does the department, Mark, you can cut this out if you want later on. I promise not to get you in trouble. But how do you know, there's a new building on campus, and how does the department shoehorn its way into a new building, get access to new campus resources and all of the local interest that's going to happen in this new, you know, $100 million building? And quantum materials has come up. And I think there was a presentation at the most recent meeting about soft matter and quantum materials. And I was thinking, you know, what could a connection in the work that I know something about be between soft matter and quantum materials? And then I thought of quantum materials, computing. I do a lot of work with LLMs for education. And I thought, well, that neuromorphic computing, when you talk to an organic electronics person, they're talking about P-dot PSS transistors on a flat substrate that are micron scaled. But a cortical neuron has like 1,000, you know, synapses, and you can't have 1,000 synapses on a two-dimensional substrate. So, but what if you had dendrimers and quantum dots and things that didn't pack into a nice lattice, but you had a 3D a 3D colloidal crystal, but not crystal, colloidal amorphous blob of stuff with multi-component things that had different appendages that made synapse-like connections. Could you do some kind of rudimentary computation with a three-dimensional sludge of conventional nanochemical objects? And so I don't know, maybe I'll go to sleep tonight and completely forget about that idea. But that's the way in which like language can lead to visualization of scientific concepts that might lead to ideas in the lab that can produce something.
So if I understand,
I don't even remember what the question was.
That's fine. So if I understand that correctly, it's kind of like an organic computer, like almost reverse engineering the brain to do these kinds of computations. Is that along the right
So
line?
there's like, yeah, so like how is integration done in the spinal cord before sensory information reaches the brain? You have primary neurons and secondary neurons that provide some gating effect. So let's say you had, I don't know, one quantum dot that absorbed light of one wavelength, and then by fret, it transferred its energy to another species, which emitted a fluorescent photon. But what if that process could be deactivated through some mechanical or chemical effect of some third type of species in the mix? You know, wouldn't that be almost like a logic gate? And so that's, you know, that's where my mind went on soft matter, neuromorphic, quantum. Maybe there's something there, maybe there's not, but that's the way I think about things.
Very nice. You know, it brings up you're talking in the process of responding to the question. I came up with an entirely different question, which is, you know, one thing that a lot of young folks struggle with, especially folks that are looking into faculty positions, is, you know, imposter syndrome and feeling like they don't belong somewhere. And you strike me as a guy who doesn't suffer from imposter syndrome at all. You know, chemist becoming the head of a chemistry department and so forth. And is that something that you ever had to struggle with? And you know, what do you recommend people do that struggle with that kind of problem?
It is absolutely something that I struggle with. I think I've already admitted like a deficiency in or at least a perceived deficiency in math and computer science. and I enjoy talking to people with that expertise, but it's definitely not expertise that I have. And I think there is a superpower to be had and not caring if you ask something dumb.
Right, right,
Okay,
right.
dumb is a bad word, but I experienced this the other day, actually. Well, last month I was in Mark's office and I asked, so has DFT been applied to catalysis before? And then on your last PodCAT, the guest said, you probably remember this, that they said it wouldn't even occur to me that no one knew that DFT had been applied to catalysis. And like,
Yeah.
you know, of course I knew that the answer was going to be yes, I guess, but yeah, and I guess Mark is the type of person who wasn't going to hold that too much against me, I guess.
Mhm.
I still got my offer letter from U of R, so I couldn't dug myself that much of a hole. But in all seriousness, I think there's a certain privilege that comes to my, position. I've been really fortunate in my life, and in many ways. Things went well for me as an assistant professor. I had some really good grad students. I got tenure fairly early. I got full professor fairly early. And I don't, if it looks like I can kind of make an idiot out of myself and say something that people are just going to say that violates the second law of thermodynamics, I hopefully don't say stuff like that very often, but there's not a huge downside risk for me at this point.
Mhm.
And so there's some security that comes from where I am in life now. Growing up, I had some of the right characteristics that I'm not responsible for, like gender, skin color, and so forth. But like my family, we were kind of poor. Like there was one year in our 1040 form after my dad passed away where we were looking through some old papers and we had an AGI on one of our tax returns in like 1991. And we got all our clothes from the church basement growing up. And when I got to college, the only reason that I went to a private school like Boston University is because they just gave me a dump truck of financial aid. And, it was all need based. And, but when I got there, like, all these people around me seemed to speak more. They talked better than I did from, a quite rural area. I say I'm from Rochester. I'm really not. I'm from a town of 5,000 people that's northwest of Rochester. And Mark, I don't know if you've ever been there, but it takes half an hour to get to my hometown. And there was kind of this articulateness of the people who I was rooming with that I didn't have. My sense of humor was, I don't know, probably a little bit coarser. Um, I, I my computer, sucked. It was a show. It was a show computer whose motherboard fried the first week of school. And in
Mhm.
fact, the way I
Oh.
learned about 9/11 was because I had my computer whose motherboard fried, and someone walked by me in the dorm room like, did you hear about what happened in New York? And I'm like, no, I don't have a computer, it's fried. And that was
Mhm.
my my the morning. And so there was a lot of imposter syndrome early on. And, I'm not sure how much different it was from plain vanilla insecurity. I think a lot of it, is contributed to, I guess, you know, struggles with anxiety later on in life. And yeah, that's where I'll land. I'll land. I said a lot there.
I, I think it's interesting to hear Ezra's perspective because I encountered, it was before we had interviewed you, or before we knew we were going to interview you for the chair position. I encountered one of your posts on Twitter that had gone viral, which was something about your NSF grant submission success or lack thereof. And it was just a post of like, I don't know how many rejections in a row, but something like 10 of them. And I think that this is becoming more of a normalized thing, that it's okay, like rejection is part of it, and it's okay if you get rejected a bunch of times. And I think your post in showing that was really resonated with me, to show that, you know, like you can have 10, 15, whatever rejected proposals in a row, and like it doesn't take too many too many, like it takes just that one break, and then things can really get better and move in the right direction. And I think that's definitely inspiring. But when you're on this kick of just multiple rejections, you can definitely feel like, does this field welcome me? Do I belong here? I can't get a grant accepted at kind of this program that's really like, once you get in, you've made it, and maybe you're not really considered to be part of the field until you get it in here. And that really did resonate with me. I much appreciated that tweet. And then later on, when you interviewed, I made the connection and I saw your Twitter and I was like, oh, it's this guy that made that post. That's great.
Hearing that now, Mark, makes me kind of feel bad that I clogged the NSF system with so many proposals that were turned down. But I appreciate you pointing that out, because when you send something like that out into the ether, you don't know how it's going to be taken. I think I mentioned something that was mildly self-deprecating on a YouTube video, and there was some dude bro who had like I don't know, a handle that had something about how much he worked out on it, and said, you shouldn't admit failure and whatever. And I'm like, maybe people are pretty uncomfortable admitting failure as a younger person because they're worried they might look weak, or maybe someone's going to review their proposals and say, well, this person got rejected, maybe it won't matter to them if they just get rejected again. But I think once you have some security, you kind of owe it to all of the insecure folks who are junior to you just to shout it out loud. Ardem Pataputian, who won the Nobel Prize a couple of years ago for discovering the piezo ion channel, his Twitter is quite, or his X or whatever, he's very open about these sorts of things too. And I think that's great for senior colleagues to do. There's one other thing I was going to say. I'll probably think of it in a minute.
So do you think, my follow-up question was going to be, what can we do as professors to kind of help to dispel these imposter syndromes that our students might have? I guess one way that you've discussed is, discussing our own journey and sharing our own experiences with others. Are there other things that we can do to help our students through these kind of struggles?
Empathy is wonderful. I have my associate dean office hours where any one of the 10,000 students and postdocs in the Jacob School at UCSD can sign up anytime they want to and talk to me. A lot of the times, those issues or the issues that are brought up are student PI conflicts. Sometimes they're not really conflicts. Sometimes they're insecurities the student has developed. Sometimes they're doing some mind reading of their advisor and some other cognitive distortions. Sometimes it's just the advisor's being an asshole, or the advisor is an asshole. And those are, I didn't ask if I could
That's fine.
use that
I guess
word.
we could, yeah. We got our first explicit episode. All right.
That's PG-13.
And sometimes those scenarios can be worked out by some rather mechanical approaches to communication, but other times they need someone to talk to, and they need to know that someone else in a position of authority and respect has actually been through something similar to what they've been through. The caveat is that society does not treat vulnerability the same across individuals, especially individuals from different backgrounds. So, for example, if women, I'm just painting with a broad stroke here, but if a young woman faculty member might be perceived a different way if they're overly vulnerable about their struggles than some gray-bearded, tenured man, although I think it's probably much less likely that the gray-bearded, tenured white man is going to admit these things, but sometimes they do. Sometimes they do.
Mhm.
So also, I kind of want to ask, we've been talking about kind of research and, but the other part of our job, right, is teaching. And when I'm, teaching a class, I kind of want to be aware, right, that maybe there are students that want to speak up, but have this imposter syndrome and they don't want to ask a dumb question. And so I always kind of feel this conundrum of, let's say I want to make it clear that I want to hear everyone's, opinions. I want to hear what everyone has to say. And so I might say to student, Y, not Y, but like student X, Y, Z, what do you think? And that could be perceived in two ways, right? It could be, me putting a student on the spot to make them uncomfortable. Usually it's me just trying to, see if that student, maybe they just need to be, invited to speak and they actually have a lot to say. And I have seen that happen quite a lot. I don't know. How do we send the right message where it's, we're trying to, be inviting, and I don't know. I always have that conundrum, and yeah. So teaching undergraduates, how do you also dispel sort of this imposter syndrome?
That is a perennial question. There are some teaching approaches like active learning or flipped classroom or peer instruction, whatever you want to call it, where you invite a lot of discussion in small groups. And so that for listeners who may not have seen this methodology, you have a pre-reading or a video that the students watch before coming to class. And then in class, you spend most of the time doing problems. The professor puts it on the board and the students work in small groups. And then maybe there's a clicker or some app-enabled thing where they vote on the right answer. And then you have them talk to each other and convince each other how things, where the logic of the correct solution wins out, and then magically 90% of the class gets the problem right after they do it individually, then they work in groups. I wasn't clear about that before. That's how it works. And so that's great for some people because they don't have to speak up in front of the entire class, but it's also very potentially be bad for students who just don't want to work in a group. I would not have thrived in that type of environment because I was just, I was so, I had so much social anxiety as a college kid. I remember I had just big armpit sweat marks that would just anytime I had to do any kind of speaking, whatsoever, and like a pounding heart kind of thing. Like if I knew what a beta blocker was at the time, I probably would have asked for a prescription. So I very much just wanted to sit in class and take notes. And then if I didn't understand something, the book was oftentimes a better teacher than the instructor anyway. And so that's how I would do it. And in some sense, I feel like a hypocrite because I love these active learning methodologies and I do them as much as I can. One way to potentially negotiate these difficulties with different levels of socialization or comfort of different students and wanting to be inclusive is that you have channels available in the class for different types of interaction with the material. I love this idea of AI textbooks, interactive textbooks, interactive tutors. Like you can program just a base model of GPT-4 with a big prompt to teach you probably what you need to know about mass and energy balances in a way that you can interact with it. And then you're interacting with something where you can get all your questions answered. But then when you go into class, you create kind of a more Maybe part of it is active learning, some of it is traditional lecturing, and you try to get the best of both worlds. But let's be honest, in a class of 30 to 200 people, students, you're going to have all kinds of learning styles and anxieties and predilections that are going to be impossible to predict. In the real world, most of the time when you're in a job in industry or policy or law or academia, you are going to need to work with people too. And that's part of why we still have college classes and not everything is done online.
Mhm. Yeah, so you
Yeah.
think it's a balance. We need to just spaghetti at the wall approach, try a bunch of different kinds of content delivery in class, and you'll get something that resonates with each student.
The students who only resonate with a particular methodology might get most of their learning from that, and that's great because you've offered it. But the students who are engaging with the material in multiple ways will actually retain it better, because the more contexts, or the greater the number of ways a concept is explained to you, the more context you see it in, the better you retain it, and the more facility you have with applying it to unfamiliar situations. So I think it's win-win. The problem is it's really hard for an assistant professor to have this kind of teaching portfolio ready to go on day one. It takes a couple of years of teaching the course to have enough material that you can actually deploy in this way.
Right, especially when you're a research active faculty and they're telling you research is the #1 priority, and you can sort of phone in the teaching and still get tenure. So getting those priorities all straightened out is a delicate and difficult balance.
Yeah. So for my example, in my example, I think the premier product that I have on YouTube is my teaching of intermolecular and surface forces. And I've recorded all of those lectures, but I started teaching the course in 2012 and I didn't record them until 2017. And I didn't do a flipped classroom until 2018. So the first year of teaching the class, I literally, because I'm cleaning my office, I literally threw away recycled that first year of notes, because I rewrote them all the next year and then taught it a few times, realized I was teaching some concepts wrong. And by the time I finally got it, I'm like, okay, I can record this now and then use the recordings in a flip classroom methodology. So there's nothing wrong with being patient about this. I do happen to think that it's easier now to generate usable at-home study aids than it has ever been before, because of electronic resources, AI, and so forth, that I would definitely encourage some of your assistant professor colleagues to become familiar with.
So we're starting to run a little short on time, and this is a Catalysis podcast, so we should spend a little bit of time discussing Catalysis. I know your research is a little bit outside of our immediate field, but maybe you can tell us a little bit about how Catalysis has impacted your work, or how it's influenced your work, or how, if you've used Catalyst in some way or another, that can maybe bridge these fields and perhaps give some of our listeners out there new, far out ideas.
Sure. The last mandate will maybe a little bit of a tall order, but I'll try to get there. The first reaction I ever did as an undergraduate researcher was a lipase resolution. And this is done all the time. Like, you take a racemic mixture of 50-50 left and right enantiomers, and you use a lipase that comes as just a powder. The key is, though, that it works in hexanes. And that was always really interesting to me, because that lipase protein is actually encapsulated by all its waters of hydration. And that's how it can survive outside the biological context. So in terms of heterogeneous catalysis, that was my first exposure. Like most organic synthetic chemists, or people who had training in organic synthetic chemistry, I did a fair number of reduction reactions with palladium on carbon catalysts, just ones that you buy from Sigma Aldrich. But then I would say that my first contribution, not to catalysis, but to, well, I don't know, to the catalysis could be interesting to medicinal chemistry type stuff. I should say, I'm only talking about heterogeneous. Homogeneous, done a lot of stuff. Metathesis polymerizations, Stille and Suzuki cross couplings, Sonogashira cross couplings, Kumada couplings, all those things that organic chemists like, but really only work on a very small scale because it's impossible to recover the catalyst in most cases. But anyway, so I had a project as a senior undergraduate, and I was staying behind in my undergraduate lab because I didn't want to move back home. And my advisor offered me $5,000 to finish a paper over the summer. And the paper was on solid acid catalyzed multi-component reactions. And so the reaction is you take an aldehyde, you take an activated amine equivalent like a carbamate or a urethane or a sulfonamide that condenses with the aldehyde with loss of the carbonyl oxygen. And the key step is that the solid acid catalyst activates that imine, that C double bond N, with another R group with a plus charge on it. And the key step is the third organic component is an allyl or crotal silane. Crotal is allyl silane, C double bond C, single bond, silicon R3. And that terminal tip of the alkene is nucleophilic against that to that activated imine. So it works with the allyl or the crotal, which is an extra methyl group. And if you have the extra methyl group and you combine this crotal silane with this activated imine, you get a product that has two stereocenters in it, which can be predicted by the stereochemistry of the silane reagent that you generated using the lipase resolution at an earlier step. So you preserve that chirality from the lipase through the final three-component condensation adduct. That type of product becomes very useful for beta amino acids, for starting materials, for various medicinal chemistry products. But my, I guess, contribution was that you could use macroporous polystyrene-bound sulfonic acids, which are used typically for ion exchange purposes in biochemistry, but you could just run these materials through a column packed with this catalyst in acetonitrile at room temperature, and out the bottom drops this three-component, highly sophisticated product, worked at room temperature, worked under ambient conditions. And we got, really interested in this process because you could rinse the catalyst out and recycle it. You could also use Nafion or Nafion particles as well. And you could pack like a pipette with the stuff, and it was so active, had such a high density of acidic sites that you could take this big liter container of starting materials and run it through this Pasteur pipette, and out pops this really sophisticated material. So that was kind of my first exposure to innovating to some kind of the most I've ever done. This was 20 years ago in the heterogeneous catalysis space, but it kind of opened my mind to just how powerful your field is.
Yeah, that's way ahead of your time, doing reactions at ambient temperature and pressure. I mean, that's what everybody's trying to do now. It's tough though.
There was no redox chemistry in there
Yeah.
at all. There was no, it wasn't very sophisticated. It's just activation of a double bond with acid. But yeah.
Yeah, I think an antioselective catalysis is a really interesting topic, especially in terms of using in completely inorganic catalysts. That's one area that I've been really interested in recently. How could we develop totally inorganic catalysts that could do enantioselective conversions, and how would we go about doing that? I think it's
There's some
area.
Yeah, in fact, your field intersects with one of the prevailing hypotheses for the origin of biological homochirality, is that some high Miller index surfaces actually have like spiral type structures in them,
Yeah.
where your materials, if they bind in a certain way, you might favor one enantiomer over the other. And if you could seed one, one type of enantiomer, maybe that could give you an S amino acid.
Yeah, exactly. I think that's a really interesting topic.
Hmm.
Yeah, it's too bad we don't have.
An ACS conference, and there was a talk about like chiral surfaces and things like that. And I
Hmm.
remember I was like, I'm going to go to that talk because I don't really know even how to think about that. And what does that mean? Like
Right.
completely new. And yeah, so
Yeah, it's too bad we don't have another hour to
yeah, there's a
get
lot of
into
stuff
this.
we
We're
could
just
talk
getting into the
about.
catalysis
Yeah.
Well,
at the
if you all
end.
join me on molecular podcasting in the coming weeks, we can make that happen.
There we
Yeah.
go.
Yeah,
Maybe
there we go.
could you tell our listeners a little bit about your podcast and what they might find over there?
Sure. It started in 2017. It started on YouTube, and it was mainly my professional development seminars that I posted on YouTube. And then I put all my course materials on there. Then in the COVID era, I took the creme de la creme of those episodes and put them on a podcast. Then I started doing some interviews as well. The podcast is called Molecular Podcasting. The YouTube channel is just my name. It's user/DJ Lapomi, or just Darren_Lapomi, bringing it to the same place. And I did a short run of a podcast called Ideas in STEM Ed, where I was during the time that I was faculty director of the Idea Engineering Student Center at UC San Diego. That's Inclusion, Diversity, Excellence, and Achievement. And we had a 20 episode run of mostly a guest kind of interview driven show on ideas in STEM Ed from a diverse range of guests. And because I'm in the middle of this career move, I haven't published a YouTube episode in a couple of months, but I was very productive in the fall and have a number that you can check out there, the most recent material. But yeah, those are the places you can find me.
Yeah, great. Well, thank you so much for coming on PodCAT. It was really a pleasure to hear from you and about your perspectives, particularly with regard to kind of this idea of access and putting all this information out there for other people to have and be able to use it to advance their own careers. So Darren, thank you so much for coming on PodCAT today.
My pleasure, and thanks for the invitation.
Yeah, absolutely. This is PodCAT signing off.